has been suggested that the electrical effect has this kind of symmetry with the law of universal gravitation. By way of review, I've written it here, that the universal gravitational force, as described by Newton here, the gravitational force is a vector, is equal to the product of the masses inversely proportional to the distance between the centers squared. And I have a universal gravitational constant and a sort of vectorness to the thing. The force is radial, and so I have an r hat. And I have a negative sign that indicates that that gravitational force is attractive. That is, if the r hat vector points radially away from the origin of my coordinate system, then the negative of that vector points toward. And so I have an attractive gravitational force, and what was suggested was that the electrical force has the same nature. That is, there's some property of matter that we call electrical charge, measured in coulombs, that describes the extent to which an object or an entity has this electrical effect. And that the electrical force that I experience in some sort of experimental preparation is according to the product of that quantity of charge and inversely proportional to the square of the distance. I have a different constant of proportionality here, K, Coulomb's constant, which is a much larger constant, 9 times 10 to the 9th Newton meters squared per Coulomb squared, that scales the effect to our universe. But also I see I have this r hat dependence. So if I squint my eyes a little bit and look at these two vector forces right next to each other, I see a kind of symmetry to it, a kind of sameness, even if it's not in all the details. It has the same sort of feel to it. And I'm going to take advantage of that to the greatest extent that I can, particularly appreciating the fact that in my classical mechanics I said that this force of gravity near the surface of the Earth could be described by a much simpler equation, one that's very familiar and probably the most completely automatic for all of us, and that is that the force of gravity, which is again a vector, is equal to mg, and I've put a harpoon on the g to signify that that is indeed a vector, and we describe that as a vector acceleration. This, of course, is the equation that we use over and over and over again, that the weight of a thing is equal to mg. We've done it 1,000 times. Well, now I want to think about that differently. First of all, I want to include harpoons on it to suggest very strongly that I'm interested in the vectorness of that quantity, but also I want to draw a parallel with the electrical effect or the electrical force. The assertion is this, that if according to the gravitational force there's some sort of gravitational field G that describes it, I wonder if I can create an equation in parallel which suggests that the electric force, again a vector, is equal to the property of matter associated with that effect. In the case of gravity, the property of matter that creates the gravitational effect, of course, is mass. But in the case of the electrical interaction, we say that it is Q, the electric charge, then multiplied by some kind of field, which describes the electrical interaction everywhere in space. Well, it's exactly what I'm going to do, and I call it capital E, the electric field. Electric field describing the electrical effect, and gravitational field describing the gravitational effect. And I have this symmetry. And you say, wow, this is excellent news because I became so familiar with the weight of an object near the surface of the Earth that I had a tendency just to sling that mg around in abandon, and solved a great many problems quite easily. Well, it's not going to be so simple, you'll find, but it's nonetheless true that I can write a symmetric equation that says that the electrical force is Q times the electric field. Keeping with this parallel, I'm going to solve these equations algebraically for their respective fields. So here, with the force of gravity, I'll simply divide the m to the other side, such that the gravitational field is equal to the gravitational force vector divided by the mass. In this sense, and this is a way that I never really thought about it when I studied classical mechanics, that the gravitational field G is equal to the force per unit mass, that is to say, gravitational force per unit mass. When we first started learning physics, very nostalgic for us now that we're already quite advanced, but if we think back to when we first encountered lowercase g, we called it the acceleration due to gravity. Well, our view of that has grown up a little bit, and we now call it the gravitational field, the gravitational force per unit mass. If I think about this in terms of dimensional analysis, this would have units of newtons per kilogram, which is something I've never done before in my instruction. I don't think anybody else has either. What I'm saying is that the acceleration due to gravity is not near the surface of the Earth is 9.8 newtons per kilogram. And we never think of it that way. Because thinking of it in the context of an acceleration and then using the units of meters per second squared is a very sensible thing when you're trying to solve kinematic problems. But now I'm trying to solve field problems, and so I could, in principle, say that the gravitational field has units of newtons per kilogram, the force per unit mass. Well, here's the symmetry of the thing again. I'll take my force, F is equal to QE, and I'll solve it around for the electric field. And for want of a better way of describing that, maybe I'll say that this is my electric field by definition, that the electric field, which is a vector field and has a value everywhere in space, more on that in just a second, but is the electric force per unit charge. The force that I observe experimentally in the nature of things divided by the intensity, the property of matter that I've invented to explain the nature of the force. So it's the force, of course in newtons, divided by the electric charge, which is in coulombs. So the units for electric field would be newtons per coulomb. And I'll find myself, at least early in this course, using those units quite commonly. It'll happen, and I'm only saying this in passing, that a little bit later in, well, just a few days actually, we'll replace these units of newtons per coulomb with units that might be more useful for our description and also for our problem solving. But for the moment, we'll think of the electric field as the force per unit charge. And to this point, it's perfectly safe, and in fact, I did it deliberately, that you're appreciating the fact that there's a force called universal gravitation that you already well understand and you've solved many problems. And here again is a force that seems to work exactly the same way. The math is there are some small differences which are easy to keep track of, but otherwise it's completely the same. Well, here's where things start to deviate. When I, as a practical matter, investigate gravitational effects, the most sophisticated thing that I might find myself talking about in classical mechanics is the motion of an entire solar system. It's true that I might consider the motion of a great number of stars in a globular cluster or in a galaxy, but when I solve those problems, I'm going to tend to do that numerically. Computers and many recipes have been created for solving those problems with large numbers of particles. But the craziest thing that I might do is consider a solar system with a star and a few planets in, where I have to keep track of the gravitational forces that act among the many planets. If you can imagine our solar system going around the planets throughout the course of an Earth year and the years of all the other objects, that they find themselves in different positions oriented around the sun. The sun itself moves a bit, but of course the sun is most of the mass of the solar system, some 99%, so the sun doesn't move much. If I want to consider the motion of an individual planet in my solar system, it's a bit of a complicated problem. I'll consider all of the forces exerted on the planet, not only by the sun, but also by all of the other planets in the solar system. But those other forces are really quite small. And I can get a very good approximation just by describing the force of gravity that acts between the sun and a single planet like the Earth. If you assume that there are no other planets in the solar system and you solve for the Earth's motion based simply on the force exerted by the sun, you get very good answers. And I need only add in the other planets for small perturbations. It's funny, I have a nostalgic memory in my head right now of when I was in elementary school. I can't say what grade. It might have been 3rd or 4th grade. And there was a great concern because someone, I guess, had written in a tabloid somewhere, and a number of people had read it and believed it, that all of the planets in the solar system were going to line up on one side of the sun, and it was going to cause some sort of cataclysmic, apocalyptic event. Well, it turns out, of course, as we all know, that day came and went, and nothing remarkable happened. Often, I guess this is referred to as a conjunction, because those forces of interaction are so small that they can be neglected in the motions and the planets just go about their business. only slightly perturbed. Well, that's the practical nature of applying universal gravitation to the problems that I care about solving. But when it comes to electrical problems, the application is significantly different, which is going to cause our treatment of this to suddenly deviate significantly. When I consider electrical effects, even the earliest electrical effects of that whole business of rubbing amber with fur, for example, there's a fantastic number of charged particles that are transferred. Not tens of planets, but potentially quadrillions of electric charges. So considering the individual forces between individual charges is going to turn out to not be a practical exercise at all. And so some new techniques, new mathematical approaches, and new ways of thinking about things are going to come into it. It's also true that on the everyday scale of things, the gravitational force is quite weak. It takes an enormous planet, such as the Earth, to create significant gravity that creates all of the, sort of earthly structure that we've created here. But the electrical force between charged particles is so significantly stronger that its influence can vary significantly on much smaller scales. For example, if we consider the gravitational force in this room, we would all be very content to imagine that the gravitational effect, that is to say the gravitational field, everywhere in the room is directed downward, straight towards the floor. Now, in a broader sense, of course, it's radially toward the center of the Earth, but in approximation, a very good approximation, in this room, the gravitational field is directed everywhere down. This is what allows us to solve free-fall problems and claim that the acceleration due to gravity is 9.8 meters per second squared everywhere and at every height, and also why we describe things as falling directly vertically downward and having no horizontal components to that acceleration. Those are approximations, but they're excellent ones. However, even in this room right now, unseen, there are electrical influences, particularly because we have created all of this technology that relies on electrical effects. The lights in the room and all the computers and all of your personal devices are creating electrical effects. And also we know that the triboelectric effect exists. So all the surfaces that rub together, for example, when you sit in your chair, electrons are being separated from their protons, and otherwise neutral charges are creating electrical effects inside the room. The electrical fields inside this room are changing on a much smaller scale. I can't even imagine what the electric field in this room looks like in general. It may have some, I think it's probably directed, is it directed downward? It might be. It's either directed downward or upward in general, but it swerves this way and that. It curves all around about the room in a complicated way. We can't solve the electrical problem of this classroom by drawing a simple approximate diagram with a uniform field. We might try to get away with that in a problem, but we'll see how that goes once we have some homework that we need to solve. But in any case, the electric field varies more dramatically, and so some care is going to have to be taken into how we think about the electric field and its value everywhere in space. So what we're going to do is, before calculating anything, and we're going to, as it happens, we're going to perform a great many integrals, but what we'll do first is we'll visualize the electric field. I have fond memories of this because when I was in graduate school for physics, I had a professor who assigned the first assignment, so you imagine it's graduate school for physics, so it's going to be some very mathematical homework assignments, and indeed there were. But the very first homework assignment was a big packet stapled together. I made 10 pages or more of just diagrams, and it was said, draw what the electric field looks like in this region of space. And the very first page was very easy to draw the electric field, and I thought, wow, this is a refreshing change from the rigors of graduate study. But then on the second page, it became a little bit more complicated, and the third page a little bit more complicated, and by the time you got to the fifth page and beyond, it was simply mind-bending to imagine what the electric field looked like in space. Let's begin with a simple example that we're already very familiar with. Consider that I have a region of space and I would like to draw the gravitational field. Well, I have an equation for the gravitational field. I just want to really quick here relate the math to it. If the gravitational field is the force per unit mass, then I might write the gravitational field this way. That the gravitational field in space is equal to the negative of gm over r squared r hat. You see, it looks very much like universal gravitation, but of course I've divided by a mass. There's a little bit of thinking here that's familiar. The m that I've written here, you can remember from when we solved gravitational problems, I made the claim that the m was the capital M was the mass of the thing that was being orbited. Well, I'm going to change that thinking just a little bit. I'm not going to change the meaning of it, but I'm just going to change the way that I talk about it and say that the M is the mass of the thing that is creating all the gravity. As I've already mentioned in the case of gravitational problems, it takes a lot of mass to create significant gravitational effects. So in that sense, the Earth is the source of gravity, and we, the poor physics practitioners on the surface, throwing projectiles around and whatnot, we're sort of the victims of that gravity ourselves as individuals, not creating a large gravitational effect. So if I were to draw the gravitational field in the vicinity of a mass, here I'll draw the mass and you can imagine that this is a planet. Well, the gravitational effect is radially towards the center of the planet. So I think there'll be a great comfort if I just draw a number of lines here. I'll just draw in a few lines. And I'll put arrowheads on each one of these lines. These lines are called field lines, and they're meant to indicate the general description of the field in space. And so you see, it's okay to use a little imagination here and to imagine that the gravitational field is crunched, directed toward the mass. Everything drawn in toward the mass, which is the field of the gravitational effect. But a few notes to keep track of here is, first of all, I can't draw all of the field. I can only draw a sample. Because, of course, the gravitational effect and therefore the gravitational field has a value everywhere in space. So to really represent it, I would have to draw an infinite number of lines, which I can't visualize because then it would just become a solid. I would just sort of black it in the whole region. So I only draw a sample of lines, but here's something a little special about it, even though it's not math, it's a diagram. Notice that the lines that I have drawn, as they head toward the mass, they converge. That is the distance between any two gravitational field lines that I've drawn, they converge. This is a general indication when I draw field diagrams that the gravitational field has increased in strength. It's generally true of the gravitational field, and we'll find that it's true as well for all other fields that we consider from here on out. When the field lines are close together, the effect is very strong. That is, the magnitude of the field is very strong, and therefore the magnitude of the forces in that region would be very, very strong. When the field lines are far apart, the field is generally weaker. So here, the field lines are convergent on the mass, and I've labeled it G with a little vector, and here's what happens. Imagine that I take a small mass m and I place it in the field. That mass m is going to, I'm being silly here, it's a little bit of preposterous fallacy. That little mass m sniffs the gravitational field in its vicinity and says, ah, that way. And according to the nature of the gravitational interaction, a mass in a gravitational field experiences a force in the direction of the field. So if I plunk a mass down at any region in space, whichever way the gravitational field points, that is the direction that the force is going to be, and therefore also, by the way, the direction of the acceleration, which is why we're comfortable not confusing, but interchanging the gravitational field with the gravitational acceleration. Well, again with the analogy, my equation for electric field is kq1 q2 over r squared. So if I'm going to write I think I may have misspoken just then. The electric force is kq1 q2 over r squared. So if I want an equation for the electric field, I'll divide by a charge. Which one? Q1 or Q2? It's very much the same issue as the gravitational issue with M1 and M2, But I want to be careful about saying lowercase q and uppercase q because in the end, as I mentioned, I'm going to be solving problems of a profusion of electric charges. And so I'm often not going to have the luxury of saying this charge is the important one and these other ones are the ones that interact. But for the moment, I'll do the same trick and say that the electric field, which is the force divided by a charge, is equal to kq over r squared r hat. That is, it points in the radial direction when the charge is positive and points in the opposite of the radial direction, that is, points inward when the charge is negative. And I've used a capital Q, but I've done it rather cavalierly. I'm content in this moment to say that the Q that I'm referring to is the charge that creates the field. So for the moment, we'll allow that, but in the future, we're going to have to be very careful about how we think about the notation as we describe the solution to problems or demonstrate some derivations of physical effects that we'd like to investigate. So what I'm going to do here, again, is I'm going to draw the electric field that I would expect in the vicinity of I'm going to choose to do it for a negative charge, because here if my electric field vector is k negative q over r squared r hat, then I'll get a field that points in the opposite of the radial direction. So when I draw it right here next to it, it's going to be very familiar. I'll draw a number of field lines. I can't draw them all. And here at the center is my charge Q, which I'll put a little negative on there to indicate that it's a negative charge. And so I put arrows on these field lines to indicate that the electric field vectors are going toward negative charge. It is a thing that you must internalize, that will be of tremendous value to you when you contemplate electrical effects and also when you're solving problems. Electric field vectors point toward negative charges. One of the ways that we say this is common associated with a lot of concepts in science and engineering. It even appears in biology, thermodynamics. Is that we call negative charges the sink, S-I-N-K, sink of electric field. Electric field lines point toward negative charges. And so the way that I imagine that this works is here I have the electric field it has a value everywhere in space around this negative charge. I haven't drawn all the lines because I can't do that, but it's representative. When the lines get closer, the electrical effect is stronger. And I see it looks very much the same as the gravitational drawing that I did for the gravitational field. And if I were to place a positive charge Q, notice I'll use a lowercase q here, just like I used a mass over here, it's the other mass. Well, now the other charge, a positive Q sets here, it will experience a force of attraction, I know, because I've already determined that when charges are opposite, the force is attractive. So leaving the field aside, ignoring the field for a moment, I know that the force of interaction here is going to be an attractive interaction. The little positive charge that I've just added to the problem will be attracted. It will feel a force of attraction toward the negative charge. I can now intellectually replace this with an equivalent idea, which is similarly absolutely essential that you internalize. Positively charged particles experience a force in the direction of electric field, just as masses, which are always positive, experience a force in the direction of the gravitational field. That's an idea that to be effective at solving problems and also at contemplating these ideas of electrical effects, you have to internalize that idea. A positively charged particle experiences a force in the direction of the electric field. Well, I have these two diagrams and everything still looks the same. Now here comes the difference. Imagine instead that I would like to draw the electric field that I would encounter in the vicinity of a positively charged particle. Well, according to my equation, the electric field vector is kq over r squared r hat. So if I have a positive charge, that field is not radially inward, but the field is directed radially outward from the positive charge. And so I've drawn here the same thing again. I have some, you have to be careful looking at these diagrams. I've drawn them next to each other, but they are not in the same physical vicinity, and that matters, as you'll see in a moment. But the electric field directed radially away. So if I place a small positive charge at this location near my charge Q, where the field is radiating away, by the way, we refer to this positive charge as being a source of electric field. I guess I'll comment on that really quickly. When I say that electric charges are the sink of electric field, you might imagine, oh, it's like a drain. The electric field is going down the drain. That might be a fun way of remembering it, but you have to be really careful. Because the field that I draw here is not in motion. It is static in space. It's got arrows on it, which intellectually, when you look at it, implies a sort of flow. And that feeling's never going to go away. Imagining that the electric field lines are actually traveling, in this case, towards the electric charge, is not true. It's an okay way of remembering it, as long as you don't use that idea to derive some sort of physical effects. A positive charge has the electric field radially out from it, and so you imagine it's the source, like it emanates, it emits electric field, which is not true. The field is completely static, but it turns out to be not a dangerous idea, imagining positive charges to be the source of electric field and to imagine that that field radiates. But please, always in the back of your mind, know that this is a static situation that we're describing. You might say, well, that makes me curious immediately about what happens when these fields become dynamic. Well, you're very right to ask that question. When the fields become dynamic, even more interesting electrical effects take place. But I hate to disappoint you, but that, of course, will come at the end of the discussion. It's one of the last aspects of this phenomenon that we'll investigate. At any rate, here I have my positively charged particle, and I have everywhere in the vicinity of that particle an electric field that radiates outward. Now I'm going to put a little positive charge, just as I did in the negative electric field example. I shouldn't say negative electric field. A negative charge is creating electric field that is radially inward. I put a positive charge there. Again here, I'll put a positive charge, and this positive charge will experience a force. According to the capital Q positive charge I put here, well, I already know, without fields, putting the field aside, I already know that if two charges are like, if they're negative and negative, or as in this case, positive and positive, the force will be a force of repulsion. And so the positively charged particle will experience a force away. Well, I've created a rule for that. I know, I've just recently said that positively charged particles experience a force in the direction of the electric field. And now that's my thinking. So what would happen if I have this positive charge here creating a field radially outward in all directions around the charge? What if I were to place a negative charge there? Well, I know, without the concept of fields, I know that it would be attractive, which means a negatively charged particle in the vicinity of this field would experience a force in the opposite the direction of the field. That's supported by the equation, and also leads me to another important rule that I must internalize. While it is true that positive charges experience a force in the direction of the electric field, negative charges experience a force opposite the direction of the field. And that's a sort of a new addition to my thinking and to my physics, because of course, in the context of universal gravitation, there's no such thing as negative charge. The gravitational interaction is always attractive. So I've got all this symmetry and all of this sameness. It's time for things to get a little bit more sophisticated. It's going to require a little bit of imagination. Drawing the electric fields that are produced by individual charges is a relatively simple task because it's symmetric and it's radial, and I can look at the equation and verify my suspicions about that. But now what I would like to consider is what would the electric field look like in a region of space where I have a positive charge, say plus Q. I'm not really going to label it. I've just made a little circle here with a plus in it. This is some positive charge. And then over here, I'll have an equal negative charge. They are equal in magnitude. The equality of those charges is going to lend symmetry to my diagram, but I suggest that you consider, and it's also true that on the internet there are many simulators which can automatically calculate and visualize the electric field in the vicinity of charges. I would suggest that you look at those. If the charges are not equal, my diagram will not be so symmetric as it's about to be. But let me draw the diagram first, and perhaps I'll come back to that idea and suggest how it might be different. In fact, I think that I will. So I have a positive charge and a negative charge, and they're in the vicinity of each other, and I want to draw as best I can. It's going to be a little bit artistic. I'm going to draw as best I can what I expect that the electric field should look like in the vicinity of these two charges. And you might say, well, Shidley, it's easy. You see, you have a positive charge here, and a positive charge is the source of electric field, and a negative charge is the sink of electric field. So what you do is you draw a line between the two of them, and you put some arrows on it, maybe two arrows, one here and one here, and you put the arrows on it that suggest that the electric field goes from the source to the sink, and there it goes, bazing, and I'm done. Well, that is absolutely true, and that is exactly what the electric field looks like on the line opposite the charges. And I might go a little bit further by suggesting that on the other side of this positive charge, the positive charge being the source of electric field, I might draw a line out here which goes away from the charge in this direction off to the left on my diagram. And I have this negative charge over here, and I'll be careful because while I draw a line off to the right there, the arrow that I'm going to put on it is toward the negative charge, and you see what I've done. The positive charge has electric field along, we'll call this the x-axis, don't we? Because so far I've only drawn horizontal parts of my diagram. So in the vicinity of the positive charge, the electric field is away, and in the vicinity of the negative charge, the electric field is toward, and everything is making perfect physical sense. Where you get into trouble is when you say, well, my goal is to know the electric field everywhere in space. So I want to determine what is the magnitude of the electric field at some point off axis, say out here, above the orientation of these two charges, and for giggles, not on the center line between the two of them. What then is the value of the electric field in space? Well, when I was studying Newton's second law, I drew a bunch of free body diagrams appreciating, according to the second law, that an object moves according to the net force that acts upon the object, that being a vector sum of the forces that act in that case. That's known as the principle of superposition. We didn't bother to give it that fancy name then, but it turns out to be true in basic Newtonian mechanics, that the net force, that an object's acceleration is proportion to the net force, which is a vector sum, a linear superposition of vector forces. I started hedging my bets there when I said that, because that is a linear vector superposition of forces that describes the motion. It turns out to be true that there are some physical systems which we have not studied, where the system moves not according to a linear vector sum, but a nonlinear vector sum. That is, the principle of superposition doesn't apply. That's called nonlinear dynamics. It's sort of a smaller offshoot of dynamics. It's a realm of physics that's often referred to in popular science, popular culture, as chaos. And we won't be addressing those issues now. But when I do a Newton's second law, I say, well, the net force that acts on the thing is the vector sum of the forces that act. Well, then if it's true for the forces, it's likely to be true for the fields, and indeed it is. That the electric field at any point in space on my diagram here is in fact a vector sum of the two contributions. So the way I'll proceed here, and just again investigating the symmetry of the thing, is I'm going to draw sort of a dotted line down the middle of my diagram that indicates the center line. And I'll consider off axis first, but I'll do it with symmetry so I don't, immediately lose my mind. Imagine I draw a point P up here that is off axis, and I want to imagine what is the magnitude and the direction of the electric field at that point in space. Well, I'm in good shape because I know how to calculate electric field. I have an equation for it. And I know the direction of the individual electric fields. So what I do is simply consider those fields separately and then vector sum the two forces with a principle of superposition. So here I have a positively charged particle here on the left, which is going to create an electric field that is radially away. I am not considering the electric field that's created by the negative charge. So I draw an electric field vector here, and I'm just going to call this electric field vector E positive, because it's the electric field vector that is created by the positive charge. And it has some magnitude because it's a particular distance, and if I was solving this as a problem, they would have given me some geometry to the thing. I could work out what the radius was and the magnitudes of the charges. I could tell you how many newtons per coulomb that field was. But now consider the charge on the right, the negative charge only, and there will be an electric field directed toward that charge, because negative charges are the sink of electric field. Its contribution points toward the charge, and I'll call that E minus, and you can see the luxury of the superposition that I've created here. They're going to have the same magnitude because they're equidistant, and I've said that they're the same charge, and so they're going to, they're going to have they're going to have the same magnitude because they're equidistant and they have the same charge. And the directions are according to my understanding of the nature of the electric field and how I draw those things fundamentally. So what will the electric field be at this position in space? Well, it's going to be the vector sum of these electric fields. Well, because of the symmetry, I can imagine what it's going to look like. It's going to look like this, the result of this parallelogram. So the electric field at point P is going to be that vector sum. So what I have to do is go around everywhere in space and work out the direction of the electric field and plot it. You might already, particularly in this more advanced age, and everybody knows how to write programs and things, you might already imagine how you could create a computer program that would do this. Well, it's already been done, and I can draw, using my age-old skill and talent, I can draw some electric field lines that are representative of the electric field in the vicinity of the charge. And you'll see appear here, as I artfully describe this, you'll see the symmetry that I referred to appearing as I draw these electric field lines. Now, it is probably true that the electric field lines that I'm drawing now were not the field lines that you maybe would have imagined. I have to add on some arrows to this, quite a few arrows. The arrows that I add on will always point radially away. See here in the vicinity of the positive charge, I create arrows that are radially away. And then in the vicinity of the negative charge, the arrows are going to point toward the negative charge, source and sink. The way that I tend to think about this is that when these two charges are in vicinity of each other, they bend each other's fields. Well, the truth of it is that there's a principle of superposition that's going on. It's a vector sum. But it's almost like they pull at each other and the fields are bent. I have these fringe fields on the far left and on the far right that bend out, and I've terminated them. They don't continue. Well, I've run out of space for my diagram. If I was willing to draw on the wall above the board here, then this field line would go up and it would be over the top and come back down around again and reconnect. So all of these field lines are emitted by the source. There again, you see what I'm saying. I create like a dynamics of it. I talk about it as if it's a kind of flow. But the field lines leave the positive charge and they terminate on the negative charge. If you see an electric field in space, chances are, not always, there's a special case. Again, comes at the end of the course. I'm sorry, what can you do? But if there's an electric field in space, somewhere there are positive charges that were the source of that electric field, and somewhere else there's a region where there's negative charges that the sink. As a matter of fact, later on we'll be having discussions and doing things where I'll say, imagine that there's an electric field, and I won't draw the sources and I won't draw the sink. I'll simply say, somewhere over here there's positive charges, somewhere over here there's negative charges, and in between there's some field, and here it is. And I'll just draw a field line and say, oh, there it is. But in general, it's true that the electric field lines are sourced from the positive charges and they sink to the negative charges, and it almost implies that I require the existence of charge, and it's not until much later on that I discover that charges are welcome but not necessary, which is really a spectacular thing. Again, spoilers. I should focus on what I have in front of me. The very next thing that I should do is draw some situation that is a little bit more contentious. Imagine that I draw two positive charges in the vicinity of each other, and I appreciate the fact now, Also, this diagram is completely separate from that one, so I'm not going to... Can you imagine trying to draw the field lines with charges? Oh, I meant to mention the magnitudes. Consider now what would happen to the symmetry of this if here I have my positive charge on the left. If I increase the magnitude of the positive charge, well, that would make the positive charge, would make the magnitude of the electric field created by the positive charge greater everywhere in space. So what I would see in my field lines is a bias that would push the overall shape of the field toward the negative charge. In a sense, I would be looking at a diagram which would, in a way, imply that the positive charge was winning because of its greater magnitude. I'm not going to draw 1,000 of these diagrams, as I say. There are simulators available where you can play with it and get a feel for how the electric field evolves in space. Even some of them give you the ability to pick up the charge and move it around in the working area of the computer program as it dynamically updates the field. But so for my last field demonstration here, I'm going to place a positive charge, and directly across from it, I'm going to place a positive charge and see if I can use a bit of imagination. It is still true that the total electric field that I get is described by a principle of superposition. So I'm going to investigate that on the center line again very quickly. So here is my center line between these two positive charges. Now, if I imagine a point directly between the two charges, sort of a special point there, what will be the magnitude of the electric field due to either charge? Well, they're the same magnitude of charge, I'm claiming, and they're equidistant from the point at which I'm observing the electric field. And so those magnitudes are going to be equal, and since both of those charges are the source of electric field, the electric fields will point in opposite directions. The total electric field at that point, directly between them, the total electric field is equal to 0. And indeed, that implies that if I was to take any other electric charge, positive or negative, and place it at that point, since the value of the electric field at that point is equal to 0, then the force experienced by a charged particle placed at that point would also be 0. Let's see if something more interesting happens further up the center line. So again, I'll investigate a point on the center line above the two charges and consider the fields. Well, now indeed there is some funny business that happens because my positive charge creates an electric field which I'll call E positive off in this direction according to the convention of the previous diagram. And it goes off like that. It has some magnitude that I can compute because in principle I know the geometry of the thing and I know the magnitudes of the charges. And this positive charge here creates an electric field that goes off this way, which has the same magnitude. So I don't feel too bad calling it E positive as well, like that. And you see what happens. The total electric field is directed along the center line, directly, say, along the y-axis, if that's how we've arranged the thing. There's an electric field directed along the center line up. So when I imagine what the electric field looks like, it's got to be 0 here at the center. And as it approaches the line, it's got to be exactly upward. So what happens, again, quite a bit of imagination needed here, is that the electric field lines sort of asymptotically approach. Thusly. And when I look at this diagram, just to give you a sense of my thinking, for whatever value that is, when I look at this diagram, it feels to me like these two charged particles are like repelling each other's field. Well, of course, the nature of the force between a positive charge and another positive charge is repulsive. And it seems to me like these field lines, boy, they just don't like each other. That's a very, I'm doing a very, what do we call it? The preposterous fallacy. I'm saying a very preposterous thing. But here are the field lines that I draw for the electric field in the vicinity of two positive charges, which ultimately repel each other. And I find that there's this region between the charges where the magnitude of the field is rarefied around the origin, where, of course, the electric field is equal to 0. And so this is what the electric fields look like. I have to stop there for my own sanity, because to draw the electric field in more complicated situations would be significantly different. But here is a very, very important point for students who are interested in being successful at solving problems of, or sophisticated problems of electrostatics and ultimately electrodynamics. It is a critically important skill for the student to have, to be able to visualize electric field. Maybe not to completely understand what it looks like everywhere in space, but to have some sense that in the vicinity of positive charge, the electric field will radiate, and in the vicinity of negative charges, the electric field will terminate, that is, source and sink. And also to know that the behavior of the charges, according to the field, positive charges experiencing a force in the direction of the electric field, and negative charges experiencing a force opposite. I don't want to be too old school or grumpy about it, but the fact of the matter is that computer programs have been designed that calculate all of these things, even in very, very complicated industrial engineering applications. The electric fields are calculated by computer. This does not diminish the fact that understanding the nature of the behavior of these things is a bit contingent on being able to at least visualize in general the way the electric fields behave in space.